Um, so, Today we talk about some basic formulas in counting, namely permutations and combinations. They are the most simple notions, which are direct applications of the rules that you saw last week. Okay. So, the talk today will be divided into three parts. First part, we established the formula for counting permutations and then combinations, and at the end we will introduce some identities, some formulas about using these terms, using the formulas for permutations and combinations. So, first, permutations are hoàn vị in Vietnamese. Okay. As usual, we start with an example. So let's say that we will have a contest, a cats, in which there are 8 cats participating in it. Okay. So the question is that if the results are decided by online voting, that means that it's sort of random, then how many possible results can we have? So now a result, we consider a result is a total ranking. That is a list of cats by popularity. So this is a possible ranking. This one is another one, and this one another one. And how many such rankings are there? If we assume that the results are completely random. So as you might have guessed already, okay. So last week we saw the product rule. So in order to determine a ranking, you will look at the first position, okay. So now, what we observe is that a ranking is a linear arrangement of the cats or of the objects or elements in the set. In general, okay? So we have a list, or we have 8 slots to fill, and we will fill the slots one by one, starting from the left and we go to the right. So the first place, we have all the cats available, so there are 8 choices, okay? So and we suppose that we choose this one, so the first slot. Then there are 7 available cats for the next, and so on. And for the third place, you have 6 available choices, and finally, by the product rule that we saw last week, we have this many possible rankings. Okay, so this is we calculate the product from the numbers from 8 down to 1. Which gives us roughly 40,000 something. Okay? And so that was an example of permutation. So whenever you have a set and you want to arrange your elements of the set in a certain order, in a linear order, then we get a permutation. Okay? So here the important word is order, okay? And you can proceed. You can use a similar argument that to the one we saw in the example about the cats, to get that we have a formula for the number of permutations of a set of n elements. Okay? So we choose the elements one by one, and we get, for the first place, we have n choices, and then we have n minus 1 choices left, and so on. And this product of the integers from 1 to n is called n factorial. Okay, so this is the notation n with an exclamation mark. Okay, and for convenience we define. So this product is defined for n for n as an positive integer, but we also defined 0 factorial as 1. Okay? So the reason is that it's more convenient for computations. So here you can see directly this is the reason for the convention that we adopt here. So if we set 0 factorial as 1, then this formula will hold for every n from 1. Okay? Because here, if we use this formula, then you can define 0 factorial as 1 factorial divided by 1, and that gives you 1. So it's similar to the reason is similar as the reason that you define like 2 to the power 0 is equal to 1. So this one is. Okay, so you have, if you arrange the whole set, then you have a commutation. And sometimes, or often, we don't have to arrange the whole set. For example, if we return to our context here, and we are only interested in the first, in the top 3 places in the context, then in this case we don't care about the losers. Okay, so we only care about the first 3 winners. So the question is that if we only count the winners, then how many possible top 3s are there? And of course we do the same. We use the same argument. We will choose the position one by one. And so for the first place we have 8 choices. For the second place we have 7 choices, and for the third place we have 6 choices, which makes a total of 336 choices by the product rule. Okay, so this one is similar, except that we only count until we have all the places that we are interested in. Okay. So this is another way. So we have found this formula. Okay. So for the top 3, the formula is 8 by 7 by 6, and we can look at it another way. Of course, since we always count the same thing, you expect to get the same result. But this is another way to look at it. Okay. So let's say that we consider let's say that we can run the contest many instances of the contest, and each time we get a full result. Each time we get a full ranking of the cats, and then we cut off after the third place, and we keep only the top 3. And by this way we can get a top 3, and we can count. So we know that there are 8 factorial results, and we get and if we list, suppose that we list all the 8 factorial results, then we can get 8 factorial top 3 like this. But here there is a problem, is that a top 3 may be obtained by many different ways. Okay? Because we are only interested in the top 3, the other 5 can be in any order. Okay? So in fact here, if we consider the same top 3 and we mix the other 5 cats, then each top 3 is is present in 5 factorial rankings. Okay, so we have repetitions with a factor of 5 factorial, which is 120 for each possible top 3. And so by the if you remember the division rule, then we can calculate the number of top 3. We can discount the repetition by taking the whole number of the rankings and divide it by this repeating factor. Okay, so in fact we can calculate the number of top 3s in another way. Okay, so either we can count, we can use the product rule and get 8 by 7 by 6, or we can use the total number of rankings and we divide by the number of repetitions for each top 3 in among the rankings, and we get this formula. Okay, and if you develop this product, then you get the same results, because this is equal to 8 times 7 times 6 and 5, 4, 3, 2, 1, and divided by, below we have 5 times 4 times 3 times 2 times 1, and you can simplify the common factor here, and you get exactly the same results as we have previously found. Okay, so we have 2 different ways to arrive to the same results. And now, after an example, we will state the general definition. Okay? So let's say that we have a set of n elements, and we want to if we take our r elements and we arrange these elements, then we obtain what we call an r permutation, or maybe in some other documents, in some other books, you can also get the name arrangement. Okay, so if you see the term arrangement, then it is the same as the term permutation here. So these terms are not unique, so it depends on the document, on the textbook, papers that you have. Okay? And here in the book of Rosen, we denote the number of permutations of R permutations of n elements as P and R. Okay. So here, note that the order is important. First, the first index n is the number of elements in the set, and the second index, the second parameter R, is the length of the R permutation. Okay, so P here, you can guess, P is for permutation, and we write this general formula. It is the formula that we have established. Okay, so you can either use the product rule. We consider the number of choices for each place. For the first place, you have n choices, and once you have fixed the first element, there are n-1 choices left, and so on. Okay, so at the R place, we have n-R plus 1 choices left, and we take the product of all we use the product rule here, and we get this number. And this number, if you want to use a nice formula, a more compact formula, then you can use this one. But if you use this formula, then you should pay attention that is the term, the product in the denominator is n minus r factorial. Okay, it is not r factorial. It's n minus r here. So So be careful here, or you can confound between n minus I or r. So for the number of r permutations, you get n minus r here in the formula. Okay? Or if you are not sure, then you can rewrite. You know how to find the formula again, so you can rewrite this and verify. And similarly, by convention, when r is 0, we set the number 0 permutation of a set as 1. Okay? It's similar to when you consider there is one empty set. So the empty set is a set, so the number of 0 permutation of the set is 1. Okay, so this is simple. This is the direct application of the product rule. Or in this case, if you want to use the division rule, it is only it's also 1 or 2 applications of the rule. So it's not complicated. Now, before we go to the next part, let us look at an application. Okay? So this is not really an application, but it is just an idea about a famous problem in computer science and optimization. Okay? So maybe some of you have heard of the traveling salesperson problem. So it is a famous NP-complete problem in optimization. And why this example shows the reason why it is a difficult problem to solve. So here, in this setting, let's look at a simple case where you have a salesman who has to travel to 8 different cities to hold conferences or to present a product. Okay. Let's say that for simplicity, let's say that this person always starts in his hometown, and from then on he can go to any town of his choice. And we suppose that all the towns are interconnected in the sense that from one town you can go to any other town. Okay? So there's no restriction. And the requirement for the trip is that this person visits each town once and only once. Okay, so he has to visit every town and not returning to any town. So you can see that from the hometown he has 7 choices to go to the next town. Okay? And once he has finished at the second town and he looks for where to go next, he has 6 choices left. Okay? And so on. And if you use the terminology of permutation, you can identify each trip with a permutation of the towns. Okay? So if you order the towns in the order of visit, then each trip will correspond for example, this one here, if we number the towns from 1, 2, 3, 4, 5, 6, 7, then this trip corresponds to the permutation 1, 2, 3, 4, 5, 6, 7. Okay? And if you go like this, then it's 1, 2, 3, 4, 5, 7, 6, and so on. So you can verify that each trip corresponds to a permutation of the towns. So the total number of possibilities is 7 factorial, which is the number of permutations of 7 towns. So this person has roughly 5,000 ways to plan to make his trip. Yes, so. And if you can try to increase the number of towns, and you can see that if you increase the number of towns just a little, then this number, the n factorial, increased very fast, even faster than exponential rate. So for a problem, suppose that you have this setting for n towns, and you want to the towns are interconnected. You can choose. You can freely choose your trip. You can freely plan the trip, but the cost of moving each of the towns are not the same. Then the traveling person problem consists in minimizing the cost of such a trip. And of course, because the number of possibilities increases very quickly, it's impossible to make an exhaustive search in the whole possible set of possible trips. So that is the reason why this problem, the traveling same person problem, is a very hard problem because of the size. We say that because of the explosion of the state space. Okay? So you can write a small program to try to calculate n factorial and to see what is the capacity, what is the limit that your personal computer can calculate. So up to which value of n can your computer calculate n factorial. Okay, so the second example involves, let's say that we want to find a pattern in a string. Suppose that you have a string made of 8 different letters, ABC, seven different letters, A, B, C, D, F, G, or let's say, okay. So if you consider all the random strings consisting of these 7 letters, then what is the probability that you get A, B, and C next to each other in this order? Sorry, I think here Okay, so this is not correct. I will fix it later. It is not 8, but it's 7 factorial. Okay, so the number is a little off here. Okay, so but the idea is that in order to count first we have to count the number of strings which contain the pattern ABC, and we divide that number by the total number of possibilities. Okay? So in order to count the number of strings that contain the pattern ABC, we can consider ABC as a single block. Okay? So in this case, if A, B, and C is considered a single block, then we have 5 elements: A, B, C, D, E, F, and G. Okay? And a string that contains ABC is none other than a permutation of these 5 blocks: A, B, C, D, E, F, and G. Okay? So if we mix these 5 elements, then we can get 5 factorial, which is equal to 120 strings. So this is the number of strings that come of 7 letters that contains the pattern ABC. So we will So sorry, the total number of string is not 8 factorial but 7 factorial. So the total number of string is 7 factorial, which is, as we saw on the previous slide, roughly 5,000 strings. So the probability will be equal to 120 divided by this. So if you want to have an estimation, so it should be roughly 240 divided by this. So that makes roughly, I don't know how many zeros. So 2.4%, okay? Around that number. Okay, so it's a little bigger than this number. So because I mistakenly used 8 instead of 7. So it should be 120 divided by 5,040. So that is about permutations, okay? Full permutations of R permutations. And now to the next part, we'll talk about combinations in Vietnamese tổ hợp. Okay? So the terms in Vietnamese for permutation is hoàn vị. For R permutation or arrangement, sometimes you see the word chỉnh hợp. And for combinations, you have the word tổ hợp. Okay, so now let us modify the format of a contest. Now we are not interested in finding the 3 winners in order. Okay, so we don't give our prizes to the first place, second place, and third place. But instead, let's say that this is just a qualification for a bigger contest. So we want to choose 3 cats to represent this town or this town in a bigger regional contest. And let's say that the team of 3 cats in that team, the order is not important. So how many possible results are there? So you can see that here the order is not important. So similarly, similar to what we saw when we count the number of R permutations in the second way, here we can see that the team, if we take the full rank and we look at the top 3, and if we choose a team from the top 3, then we see that a team can be obtained by 6 different kind of top 3s. Okay? So we can use the division rule here to find out the number of teams here is equal to the number of top 3s divided by the factor of repetition here. Since you can mix up the order of these 3 cats, you get 6 repetitions. So the number is much smaller than the number of possible top 3. So here we have 8 cats and we want to choose 3, and the result is is 56 possible teams of 3. Okay, so whenever we talk about whenever we consider the number of choices in which the order doesn't matter. We talk about combination. Okay? So in the set terminology, in fact, you can consider an R combination of a set of n. You can identify an R combination as a subset of n elements, of R elements of that set. Okay? So R combination is equivalent to a subset of size R of R elements. Okay? So here the underlying word is unordered. So this is the remark that distinguishes this case with the case of permutations. Okay? So we can repeat the process that we established to count the number of teams of 3 cats. So here it's exactly the same, except that we replace the numbers 8 and 3 by the general numbers n and r, and we get and the number of r combinations is denoted by C and R. Okay, C for combination. You can easily guess, or you can you can use either this notation C and R, which is easier to type, or you can use this notation which is red and choose R. Okay. And the formula for the number of R combinations of n element is given by this formula. You have n factorial divided by r factorial times n minus r factorial. And so if you separate this term n factorial divided by n minus r factorial, you get the number of r permutations. Okay, so you can view this as the number of r permutations divided by the number of permutations of r elements. So I provide here a sketch of proof by using a double counting argument. So in this proof and in many exercises, as well as in the formulas, the identities that we will see later, we use a lot of double counting arguments. So what does double counting mean? Double counting means that in order to establish an equality, you count something in 2 different ways. Okay, if you count something in 2 different ways, you may obtain 2 different formulas. Well, of course, since you count the same things, these formulas must be the same. Okay? So here, what we will count 2 times is the number of r permutations of n elements. Okay? So the first way is what we have already done. If we count the first way, then in the first way we use the formula that we have established, and we know that the number of r permutation is p and r. Okay? And so in order to count the number of r permutations in a second way, we will use this process consisting of 2 steps. Okay? So previously we have chosen the elements one by one. Okay? But now we will do the reverse. We will choose all the r elements first. Okay? So if we choose r elements from a set of n, then we get n choose r ways. Okay? Because it is the definition of combinations. Okay, so if we are, so for the first step, but now, since in order to create an R permutation, we have to take into account the order elements. So we need to arrange these R elements. Okay. So remember that now we choose R elements, but we haven't arranged them. So now in step 2, what we already have R elements, we will arrange them. That means that we will choose a permutation of these R elements. So you know that for R elements there are R factorial permutations, R factorial ways to arrange these elements. So this is a sequential procedure. So we apply the product rule, and we get the number of ways to do the first step times the number of ways to do the second step. We get this term. Okay. So if we use this process to count the R permutations of n elements, then we get this result. But of course, it must be equal to the number of R permutations that we have already counted. So we have this equality, and now we can divide both sides by R factorial, and we change sides, so we get the n choose R is equal to the number of permutations of the number of R permutations of n divided by R factorial, and we will plug the formula for R permutations here and get this. So this is a simple example that illustrates the use of a double counting argument to prove an identity. Okay? So this is true. This is true for any for any positive integer n, and for any integer r not exceeding n. Okay. Now consider this example. So suppose that you play with a standard deck of cards, of 52 cards, and you want to deal a hand of 5 cards. Then, what is the number of different hands can you get? Okay. So here, when you consider a hand of 5, there is no order. Okay. Since there is no order, we use combination instead of permutation. Okay? So here you have a deck of 52 cards, and you want to choose 5 without order. That means that the result is 52 choose 5, and we plug the formula to get this. And here, pay attention to this. In order to calculate this number, you do not calculate 52 factorial, okay? 52 factorial is a huge number. You cannot calculate it with your computer, but here you should be clever. You should be more clever. So, we do not calculate 52 factorial, but we simplify first. So what do we simplify? Do we simplify by 5 factorial or 47 factorial? We will simplify by the bigger factor. So this one, we do not calculate 52 factorial, but we write it. We will simplify the 52 factorial. In fact, you can write it as 52 times 51 times 50 times 49 times 48 and times 47 factorial. Okay? So this way you can get rid of 47 factorial. And what you get is a much more reasonable product to calculate. Okay, and this one you can use your pocket calculator to find the results. Okay, so the point here is that you should simplify this before you do the calculation. Okay, never ever calculate this astronomical number. Okay, so the second question asks how many ways are there to select 47 cards. Of course, you do the same. Here we change the row, so we have 52 choose 47. Okay. But if you write out the formula, then you see that it's exactly the same. You simply exchange the row of 5 and 47. And so here, since you have already had the result above, you don't have to do the calculation again, and you get the same result. Okay? So in general, if you exchange, if you exchange the row of R and N minus R, the result is the same. You can see this in the you may have already noticed this in the formula here. Here you can see there is a symmetry between N and N minus R. So here if you replace R by N minus R, then the right hand side remains the same. Okay, so we have this. And of course, this comes directly from the formula, but it can also be deduced from the remark that each time you take out a subset of size R, you have created a subset of size N minus R, which consists of what remains. Okay? So in fact here there is a one-to-one correspondence between the subset of size R and the subset of size N minus R. Whenever you cut a set of size N in two, and you take out the one part of size R, then the other part is of size N, so it's symmetric. You can see that it's the same whether you choose N elements or choose N minus R elements. Okay, so this one-to-one correspondence is also called bijection summing. Okay, so in some counting problem, if you can establish a one-to-one correspondence or a bijection between two sets, then you can say that the number of elements of the two sets are the same. They have the same number of elements. Okay? So here if we make the correspondence between each set of size R and its complement of size N minus R, then we have a one-to-one correspondence between the R combinations and the N minus R combinations. Okay, so you can derive this formula in two ways. Either you can use the direct formula, or you can think of a bijection between the subset of size R and the subset of size N minus R. Okay, so here we conclude this part on combinations by an example, a still simple, but with more steps. An example. So suppose that you have two departments, applied math and computer science. And in one department you have 9 lecturers, and in the other department you have 11 lecturers. So now you want to elect a committee to develop some program. So you want to choose 3 members from the math department and 4 members from the CS department. So how many possibilities are there for this committee? So when you want to count the possibilities, you have to think of a way, how can you form such a committee? So your committee must have 3 mathematicians and 4 computer scientists. So how do you choose? If you are the one to choose, how do you choose such a committee? So of course, it is common sense to choose the 3 members of the math department and the 4 members of the computer science department separately. Okay? So the first step, you choose the 3 mathematicians. And among 9 lecturers, if you choose 3, then you have 9 choose 3 ways. Okay? In the second step, you have 11 choose 4 ways to choose the representatives for the computer science department. Okay? So now you have 2 steps which follows each other. So by the product rule, you get this number. So you get the product, and so I let you do the calculations. So I hope that what I did here is correct. So roughly you have this many possibilities for the committee. If you have no restriction, if you post no restriction on the choices of the members. Okay, so that was the easier part of today's lecture. I propose we take a 5-minute break, and after that we will talk about identities, formulas, and so on. So I put the slides on Moodle, but since there was some mistake, don't download the slide yet. Okay, so wait a little bit so that I correct the mistakes in the example. So, sometimes you can see the numbers of combinations called the binomial coefficients, hệ số nhị thức in Vietnamese. Okay? So the reason is that they appear in this famous formula, which is called, sometimes you can see the Newton's formula or binomial formula or Newton's binomial formula, công thức nhị thức Newton. Okay? So it is the formula that gives you the development of this power of the sum of two variables. Okay, so you have x, if you develop x plus y to the power n, then you get the sum. And you can see that the number of combinations are involved here. They are the coefficients corresponding to the terms x to the power n, x to the power n minus 1y, and so on. Okay? So you can see here there is a pattern. Okay? So these numbers are also called the binomial coefficients. So if you see binomial coefficients, then you understand that it is the number of combinations. Okay? And okay, so I guess that you are familiar with this development. But here we will see the derivation of this formula by the combinatoric arguments. So here, as some example, if we develop x plus y to the power n for some small value of n, we can verify that. So here, if n is equal to 1, we have two terms. Okay? So this term here, you can see that the indices below run from 0 to n. Okay? So for n, there are n plus 1 terms on the right hand side. So here, n is equal to 1, you have two terms in the sum. For n equal to 2, you have 3 terms. And for n equal to 5, you have 6 terms. Okay? So here you can verify that 1 choose 0 is always 1. Okay? So here the first and the last coefficients are always 1 because n choose 0 is 1 and n choose n is 1. Okay? So what is the meaning of n choose 0? N choose 0 is the number of subsets with 0 elements. Okay? And you know that for any set, there is one and only one subset of 0 element, which is the empty set. And similarly, there is one and only one subset with every element, which is the big set itself. Okay? So the first and the last coefficients are always 1. And you can clearly see here. So here, for the case n equal to 5, you can calculate. So 5 choose 0 is 1. 5 choose 1 is 5, because if you have a set of 5 elements, and then there are 5 ways to choose one of those elements. And there is some symmetry here. Because of the remark of the corollary that we saw here, because of this, you can see that there is a symmetry in our formula. So here, for example, you can see the first term and the last term are the same. The second term and the second to last term are the same. And similarly, so if you go from the left to the right and the right to the left, and each time you advance by one term, then you always have pairs of equal coefficients. Okay, so here you have 1 and 1, 5 and 5, and 10 and 10. Here you have 1 and 1, and in the middle 2. Okay, so it's the same. So how can we prove this identity? So one way to prove is by using induction on n. So we know what induction is. Quinat. So you see that this formula is true for some small values of n. So if you can prove that, so the idea in induction is that you suppose that our formula is true from 1 to n. Then you show that if it is true from 1 to n, then it is true for n minus 1. If that is correct, then you can combine with the initial conditions. You know that is true for 1, so it must be true for 2. Then for 2 is true, then it's also true for 3, and from 3 to 4 and so on. Also, that's the idea of induction. Okay. So yeah, if you want to have an algebraic proof, then you can use induction. Then you can use you can write out the algebraic formula. But here I introduce another way to prove by a combinatorial argument. Okay. So here let's look at the case for n equal to 3. And we are interested in the terms of this form, for example. Okay? So if we write x plus y to the power 3 as the product of 3 expressions, 3 sums like this one, then you can see that each time you choose one of the 2 terms in a sum, and one of the 2 terms in another sum, and one of the 2 terms in another sum, and you combine them together. Here the both. So here suppose that you choose x in the first sum, y in the second sum, and y in the third sum. Then you have a product of x, y, and y here. And you get one time the term x, y squared. Okay? So you can create one term x, y squared in another way. For example, here you can choose y from the first sum, x from the second sum, and y from the third sum. So in this case you have y times x times y, and you can rearrange to get the same. And similarly you can choose y, and x, and you get the same. And those are the only 3 ways to get this combination. So each way will give you one such term. So there are 3 ways to get 3 terms. Okay? So x y squared plus x y squared plus x y squared gives you a coefficient of 3. And what is the 3? Coincidentally, 3. In fact, here, in order to have this term, you have to choose x one time. Okay? So you choose x from one of the sums, and you choose y from 2 other sums. Okay? So in fact, each term x y squared here corresponds to a way to choose 1x and 2y. Okay? So here you have 3. So the number of ways to choose 1x and 2y among 3 sums is equal to 3 choose 1, or equivalently 3 choose 2. Okay, so if we generalize to the general case here, okay, so the general term on the right hand side has the form x to the power n minus I, y to the power I. This corresponds to the one occurrence of this term on the right hand side, correspond to one way to choose x from n minus y sums at x plus y, and you choose I y from the rest. Okay, so it's written here. But if this is too abstract for you, you can always give you a concrete example here, so you can see, you can visualize. So here I use n equal to 3 because there is not enough space. If you use, for example, n equal to 5 and I equal to 2, then you get 10 times, 10 ways. So it's a little long to list all the ways. So here it is in the wrong. So here this is the general description. Okay? So when you develop here, in fact you have these generic terms on the right hand side, and each term corresponds to one way to choose this many x and this many y's from the sums, from the n sums on the left hand side. Okay? And you know that the number of ways to choose exactly n minus y x and I y's is equal to this. And symmetric, since it's symmetric, is also equal to this. And so there are n choose n minus y times this term on the right hand side. So you group them together to get n choose n minus y times this product. Okay? And you do that for any value of I going from 0 to n, and you get the full development on the right hand side. Okay, so if you don't like, you can always use induction, but by using induction, it is pure algebraic. I'm not interested in proof by induction because in this course we talk about combinatorics. So combinatorial proofs are more interesting. Now, as practice, now it's your turn to. So I give you this this product. So please give me use the formula to find the coefficients of this term x to the 6th and y squared in the expansion in the development of this product. Okay. So write quickly. So here what is n? N is equal to 8, I is equal to 2. Okay, so you can plug in the formula. So the coefficient is 8 choose 2 or 8 choose 6. It's the same. Okay, so it's simply this, and you can for small numbers like this one, you can. So this is equal to 8 times 7 divided by 2. Which gives you 28. Okay, on to the next example. We have a bigger power here, 25. So in this example, you do not need to write the exact number, but you only have to write the formula. Okay. So here is a little bit more complicated because there are some the coefficients of x and y inside the parentheses are not ones, but you have 2 here, 3 here, and even a minus sign here. So you need to pay attention to the sign. Okay? So find me the coefficient of this term in this expansion. You got the result? And so here, if you are not familiar with this, you can write 2x as a minus 3y to the 25 as first you write it's a big X plus big Y to the 25 with big X equal to 2x and big Y equal to minus 3 small y. So the coefficients corresponding to the powers 12 and 13 is 25 choose 12, okay? Big X to the power 12, big Y to the power 13, okay? And now you replace, here you have 25 choose 12 times, you replace big X with 2 small x to the power 12 and then minus 3 small y to the power 13, okay? Then you get this, okay? So 25 choose 12 give you this, and here you have a minus sign with an odd power, so you have a minus sign in the results, and here you have 2 to the power 12 times 3 to the power 13. Okay, now let's look at some special cases. So here you have the general formula, but now we will try to replace to plug special values of x and y in here to see what we can get. So the first thing is that if we let x and y be both equal to 1, then what do we get here? So if x and y are both equal to 1, then on the left hand side we will get 2 to the power n. Okay? And since x and y are 1s, every monom here are equal to 1. So you don't have x to the power n anymore. So you only have a sum of binomial coefficients. So when x and y are equal to 1, you get this one. So here I have switched the sides, the two sides. Okay, so this was the left hand side. This was 1 plus 1 to the power n. So you can verify this. So this is a familiar formula. Okay, so it gives you the number of subsets. So if you haven't forgotten what we talked about last week, you will notice that on the right hand side here, 2 to the power n is the number of subsets of a set of n elements. Okay? So what is the relation y? So that gives us an idea to relate the two expressions on the left hand side and the right hand side. So if we consider a set of n elements, then the right hand side counts the number of subsets. Okay? And here on the left hand side, it is also the number of subsets, but counted in a different way. Which way? In fact, each term here, n choose y, is the number of subsets of size I. Okay? So if you consider a set of n elements, let's say, so without loss of generality, we can say that if we consider this subset of n elements, we want to count all the subsets of this set. So if we count by, we will classify the subsets by size. Okay, so we count the subset of 0 elements of size 0. How many such subsets do we have? We have, by definition, n choose 0. Okay? So subset of size 1, we have n choose 1. So for subset of size 2, we have n choose 2, and so on. So if we consider the subset by size, then the left-hand side is exactly equal to the total number of subset of size 0 plus subset of size 1 plus subset of size 2, and so on. But since every subset of our set of n elements must have a size between 0 and n, this left-hand side in fact counts all the subsets. Okay? So here we have two ways of counting the number of subsets of a set of n elements. So that gives us this identity. So this identity is, once again you have two ways to prove this identity. Either you let x and y be equal to 1 in the Newton formula, or you use a double counting argument. This way you count the number of subsets. Okay? So you have two ways to prove this identity. Okay, so here, so if we let x and y both equal to 1, you get this identity. And now we can also let one be minus 1 and the other be 1. In this case, the left-hand side of the Newton formula becomes 0, okay, because x plus y is equal to 0. And on the right-hand side, you have a sum of alternate signs in terms of signs plus and minus, plus and minus, plus and minus, and so on. Why? So you can write, for example, the detailed formula for the case, let's say n equal to 6, okay? So if n is equal to 6, you have minus 1 plus 1 to the power 6, which should be equal to 6 plus 6 choose 0 minus 1 to the power 6 plus 6 choose 1 minus 1 to the power 5 times 1. Okay, and then you have 6 choose 2 minus 1 to the power 4, 1 squared, and so on. So here if I is odd, then you have a minus sign. And if I is even, then you have plus. So if you put all the plus on one side and all the minus on one side, you get 6 choose 0 plus 6 choose 2. So here I let you complete the line. Okay, so plus 6 choose 4 plus 6 choose 6. And on the other side you have 6 choose 1 plus 6 choose 3 plus 6 choose 5. Okay? So the bottom line is that here in the Newton formula, if you let x be minus 1 and y be 1, you write the formula and then you put all the terms with the plus sign on one side and the minus terms on the other side, then you get an equality like this. You have the sum of binomial coefficients corresponding to even indices is equal to the sum of coefficients of binomial coefficients corresponding to odd indices. Okay? So sometimes there are more on one side. Okay, so here you have 0, 2, 4, 6, and so on. Here you have 1, 3, 5, and so on. And you can try to write similar for identities for other values of n, small n's, for example 5 or 4 or 7, to get a hang of it. Okay, so about binomial coefficients, there is also an interesting identity that allows you to obtain what is called the Pascal triangle. Okay. So you all know the Pascal triangle. Yeah. So this identity is like this. So here you, if we write the general identity, then it involves three terms, three binomial coefficients. And here you notice that the size of the set on the left hand side is n plus 1. And the size of the set on the right hand side is n. Okay? So this identity relates binomial coefficients, let's say of an upper level, of level n plus 1, as the sum of two terms of the level, next level below it. Okay? And the index here are similar, so it's k here and k minus 1 and k here. So of course you can use the formula for binomial coefficient to prove this directly. Okay? You can write it and use some algebraic calculation. So you can write it as n plus 1 factorial divided by k factorial n plus 1 minus k factorial, and you are on the other side you have this. Okay. So after some simplification, you can arrive at the conclusion that the two sides are the same. Okay. So you can use the definition to prove that they are indeed the same. But so that way of proof is easy. So I will let you do it yourself. So here I will present with you a more interesting proof based on a combinatorial argument. Okay, so once again we count something in two different ways. So on the left hand side it is direct. Okay, so we consider a set of size n plus 1, and without loss of generality we suppose that it is a set of integers from 1 to n plus 1. And with this set, we know directly that this term on the left-hand side is the number of subsets of size k of our set S. Okay? So that is the definition of binomial coefficients. Now, we need to count this number. We need to divide the subsets of size k of this set into two cases. Okay? Into two cases here. We have a sum. So we want to use the sum rule. We need two separate cases so that in one case we have this many subsets, and in the other case we have this many subsets. Okay, so what do we use? So in fact, we distinguish the two cases by isolating the one element of the set S. So without loss of generality, let's say that we look at the element n plus 1. Okay? So now, if we consider subsets of size k of this set S, such a subset can either contain n plus 1 or not. Okay? So if it contains n plus 1, how can we construct such a subset? Okay, so we have something of size k. So I will distinguish, so if it contains n plus 1, contains n plus 1, so it is a question. So if the answer is positive, then we go to one case. If the answer is negative, then we go to another case. Okay? So if it contains n plus 1, and we want it to be a subset of size k, then we have to choose the other k minus 1 elements. Okay? Because one element is already n plus 1, we only have k minus 1 choices left. So we need to choose the other k minus 1 elements. And of course we choose the other k minus 1 element from the n elements left. Okay, so from 1 to n, because we have taken out n plus 1. Okay, so if we choose this many elements, then we have n choose k minus 1 choices. Okay? And now, the other case is that our subset doesn't contain n plus 1. That means that in this case, instead of choosing k minus 1, we need to choose k elements from 1 to n. And so we have n choose k. Okay? So now, if we look at this diagram, we have separated the subsets of size k of our set from 1 to n plus 1 into two subcases. Okay, so so two separate categories. In the first one, we have n choose k minus 1 subsets, and in the second one, we have n choose k subset. So by the sum rule, we take the sum of these two, and we get the total number of subsets of size k, like our set from 1 to n minus 1, n plus 1. Okay. So to summarize, both sides count the number of subsets of size k of this set S. So they must be the same. Okay. And now if we use this formula, then we can get something interesting, okay? So now our triangle grows from downwards, from top to bottom, okay? So here each level corresponds to one value of n. So here you have n equal to 0, here you have n equal to 1, n equal to 2, and so on. And you use the Pascal's identity that we have just proven is illustrated by those small triangles here. Okay? So you can see that the Pascal identity. This is an example for n equal to 6, n equals 6, and k equal 5. Okay. So this identity, you can visualize this. This means that if you take two terms on level 6 here, and you calculate the sum, then you obtain the term below and between the two terms here on the 7th row. And in this way, if you start with, and of course in each row you start with the ones from the outside. Okay. So row 0 you have one term, row 1 you have two terms, and so on. So here you have 1 and 1, and the middle term here you obtain by taking the sum of 1 plus 1, that gives 2. And here once you have the second row, the row corresponding to n equal 2, you have 1 on the left and 1 on the right, and in the middle you have 1 plus 2, that gives you 3, and 2 plus 1, that gives you 3. So here similarly, once you have row 3, you get 1 plus 3, 3 plus 3, 3 plus 1, and so on. Okay? So you can go on as you like to calculate the rows. So this you can use this identity. Once you don't need to know the rows above. You only need one row in order to calculate all the rows below it. Okay? Okay, so we can now the next identity is a little more involved. That is, it is a sum, but not a sum of simple terms, but a sum of products. Okay, so here you have more parameters. So instead of n and k, you have another parameter n. Okay. So here the idea is that. So here I don't know if you can. I think that you can use the formula and you can brute force it by algebraic calculation, but it will be nicer if we find a combinatorial argument. So here once again we will try to count something in two different ways. Okay. So here of course the left hand side is kind of obvious, so it suggests that we count the number of subsets of size R of a set of n plus n elements. Okay. So here from this factorization you can guess the idea is that you divide your set of n plus n elements into two halves, and you create your subset of size R by taking one part in the m half and the other part in the n half. So basically the idea is this. It would be more intuitive if you draw a diagram. So here you have a set of size, a big set of size n plus n, that you can suppose that it has a left part has n elements and the right part has n elements. Okay, so you want to choose a subset of size R from this set. And any subset of size R you can decompose it into two parts. One part is included in this side, on the left hand side, and the other part is included on the right hand side. So suppose that you have I here, so that means you have R minus I left on the, so let's call this A, the part A of size M, and let's call this the part B of size M. Okay? So any subset of size R can be viewed as a subset of size I of A combined with a subset of size R minus I of B. Okay? So here you can see that, I must switch I and R minus I, so that corresponds to the formula. Okay? So here, if you look at this diagram, then you can see that the number of ways to choose this part, smaller part of R minus I element on the right hand side is this. Okay? And the number of ways to choose I, a subset of size I from B is this. Okay? So you choose two parts, one after another. So here we apply the product rule, and we get this term inside the sum. And since our I can get any value from 0 to R, we have R plus 1 cases, okay, for I equal to 0, for I equal to 1, and so on. And we apply the sum rule, and so finally, so here if we fix I equal to 0, this will correspond to the number of ways to choose a subset of size R inside this left part, and an empty set on the right part, and so on. Okay, so it is written here on the slide. There is no diagram, so if you like, you can copy this diagram here, and it will help you understand the proof more easily. Okay. So in fact, the formula looks complicated, but if you get the idea of what to count, then the idea is pretty simple. And this formula is simply the translation of the idea into the language of algebraic language, into the formula. Okay. So here, once again, if we do something similar to the as we did with the Newton formula, we can get some interesting results. That means that here, if we consider the special case where n and r have the same value, okay? If we let r and m be equal to n, then we get this. I will rewrite it here. So if m is equal to n, then and r is also equal to n, then the left hand side is 2n choose n, okay? And the right hand side is the sum with I going from 0 to n, n minus I, and times n choose I, okay? But you know that these two are the same, symmetry, so if you replace this is equal to n choose I. So in the end, it will become n choose I squared. And you get this identity. Okay? And okay, so this formula, the proof is a little. I will leave this formula for next week, okay? Because the proof needs a little bit of explanation and times is also up. So I fixed the slides so you can download the slides now. It's available on YouTube.
Các bạn học các bài tập chưa?
Còn những cái gì, những cái chứng minh, những cái gì về bài học mà các bạn còn chưa hiểu ngay